So we're gonna do something a little different today. We're not exactly gonna be discussing math, um, but nonetheless, it's got something to do with tops and bottoms. Again, like I keep talking about this stuff, and it just when we when um, when I did position theory, right? It's great. It was great and all this stuff, but um, it'd be nice if we try to actually apply this, or if we use some really concrete concepts, grounded, in physics. Not just classical physics or quantum mechanics, but quantum electrodynamics, or QED. Most notably, the standard model. So, the standard model. Excuse me. So the standard model is the best scientific theory that can explain what makes up matter in today's society, or in modern times. It's the best explanation we have for why we have electromagnetic waves, how we have light, how we exist, of course, but not our origins, of course, but nonetheless, what matter is made of. So, the notion before was that we just had the most irreducible form, or the most irreducible thing that makes up matter are atoms. So you have these things with little tiny stuff in them, like neutrons and protons, and then we have an electron zooming around. And then, more electrons and then more protons or stuff like that determines what element the particle makes up. Okay, that makes sense. Or, not particle, but same. Yeah, element, what element it is, right? So the amount of protons inside it gives us what element is it. Okay. But then we realize now that the things that make up an atom, these protons, are actually made up of new things, tinier, smaller things, which we now call elementary particles. Now it's still being debated, well, at least as of the making of this lecture, it's still being debated whether these elementary particles are actually particles or strings that propagate through space, and the vibration of the spring gives us the properties of the supposed particle we have. But in the case of quantum electrodynamics and the standard model, these elementary particles are just points in time, dimensionless points. Elementary particles. And there are many of these elementary particles, but they are separated into two main groups, which are the fermions and the bosons. So the fermions are split into two main types here. And the bosons here are what mediates various forces between the fermions. So the fermions are composed of, the fermions contain or branch out to different things, namely the quarks and the gluons. Or I think the gluons is under the bosons, but it's sort of the categorization of all these elementary particles are a bit confusing. And so quarks and gluons. So quarks are the primary things that make up things. They're the actual structure of the protons or other particles that make up atoms. While gluons are the particles that mediate a strong interaction force which keep the quarks together. Now bosons, on the other hand, are different, wildly different, because bosons' primary purposes are either to, actually this also includes the photon in fermions. photons. Okay, so bosons now mediate some other forces such as electromagnetic forces and the opposite of the strong nuclear force, which is the weak nuclear force. So that's what bosons do. And also, yeah. So quarks now, which is the primary focus of today's lecture, or today's short lecture, is mainly separated into four, or actually five, I believe. So we have the top quark, the bottom quark, we have the charm quark, we have the up quark, the down quark, and the strange quark. But because I'm only going to be talking about tops and bottoms today, we're only going to be focusing on the top and bottom quarks. Now, bosons, now there are many types of bosons here. There is the WZ boson, the W plus boson, and the W minus boson. Okay. So these elementary particles have various properties such as spin. They also have, of course, mass. But mass in the case of quantum electrodynamics is not measured in kilograms, but rather mega electron volts per the speed of light squared. So that's the measurement for mass when it comes to these elementary particles. Spin, on the other hand, is a fixed constant, and it determines some abstract notion that is somewhat but not directly related to actual, spinning, like angular momentum. So, yeah, so this is mass. Sometimes it's expressed in giga electron volts, depending really. Sometimes physicists just emit this c squared term or 1 over c squared term and just say mega electron volts. But when we're talking about mass of elementary particles, this is usually meant. Okay. So the primary focus of, again, as I said, the primary focus of today's lecture or today's short video is to focus on the top and bottom quark. So before we start talking about the top and bottom quark and why tops can be bottoms, but bottoms can never be tops, let's talk about the second law of thermodynamics. The second law of thermodynamics. Now the second law of thermodynamics states that energy can neither be created nor destroyed, just transferred. So if I have a system, let's say I have a system over here, let's call it denoted alpha. Let's say I have a system that is endowed with, let's say, 3,000 watts of energy. I'm using watts instead of joules, that's right. So let's say that its total energy is 3,000 watts. Or, you know what? Let's say that its potential energy is 3,000 watts. Yeah. And then we let this system evolve over time, and then we end up with 0 watts, of course, of potential energy. So PE, and then PE, PE 0, and then PEF for final, is 0. And so now our kinetic energy, let's say that, of course, this is an ideal environment and all that. We don't lose energy. Absolutely not. So our kinetic energy now in the end, our final kinetic energy, would be 3,000 watts as well. Because in this ideal situation, all of the potential energy transfers into kinetic energy. Now notice how, of course this is minus 3,000, because what we want is that our total energy stays within, or doesn't exceed 3,000 watts, or doesn't go below minus 3,000 watts. So it would make sense that our total energy would be 0 in this case. Now do correct me if I'm wrong here, because it's been a while since I read physics. Okay. Okay, so what I'm trying to illustrate here is that we never gain any energy by letting this system evolve over time because we never touched it. Okay? Let's say that this system over here is a particle traveling through space. It's a particle that's moving in this vector, or using this vector. Alright? Now, we don't do anything to the particle. We don't add energy to it. We don't direct it or change its direction via electromagnetic coils or anything. We don't do any of that. We let the particle travel. We let it travel and don't change its velocity. We don't accelerate it or do anything to it. This should follow. The second law of thermodynamics should follow, and it will soon lose energy. Or, well, this is for a system that's rolling down a hill, or gradually gaining speed, or gaining velocity, right? But for here, right, we give it some velocity, right? Some initial velocity, it's traveling, and then soon, via some natural force, it's gonna slow down. Because it's transferring its energy, or it's transferring all its energy, or its potential energy into the universe. Or its kinetic energy, rather. It loses kinetic energy and then it stops, and then it instead has potential energy again. So it doesn't really gain it, but rather the energy transfers from the environment to the particle. Once it stops, of course. Okay, or it rather transfers. It transitions from kinetic energy or potential energy to kinetic energy, and then kinetic energy back to potential energy. Okay, so that's the second law of thermodynamics. We cannot add energy to the universe, or we cannot remove energy from the universe. We can merely transfer energy in the universe from one point to another. And even though we may not know it now, but the total energy of the universe will remain constant. We will never add anything to it or remove any from it. It will remain the same, and things will just balance out in terms of what is transferred and what is taken, what is left over, or what is taken. What is taken and what is left over. It just balances out. Okay. Now there's a possibility, because of how disturbing reality is, that maybe the total energy of the universe may not be as we thought it would be. That maybe it would change when we change something significant. But as for the current time, or as for the time being, this law holds. And that this is the reason why perpetual motion machines cannot exist. Okay, so now let's talk about top and bottoms. Tops and bottoms. Most notably, if we treat people as elementary particles, such as the top and bottom quark. Suppose that a top person, or a person who's inherently a top, is a quark. And let's suppose that another person is inherently a bottom, but is a quark. Now, it is known that top quarks have a 98% chance of turning into a bottom quark. Okay? So this thing is called decay, and if I just get my notes here. Yeah. So, okay. It has 98% chance of turning into a bottom now. But the thing is, top quarks have more energy or more mass than a bottom quark. In fact, the top quark is the heaviest one among all quarks. Among the strange, the charm, the up, the down, and the bottom quarks, the top quark is the one with the most mass. And the bottom quark now has less mass than the top quark. It is one of the lightest It is one of the lightest quarks among all quarks, or yeah. And so, that's sort of the reason why, or that's the bottom line on why bottom quarks cannot turn into top quarks. Because they have lower energy, or actually lower mass, and it would require us to add mass to the bottom quark in order for it to become a top quark. It cannot just decay into a top quark on its own. So actually, we don't say turning here, but we say it decays. So decaying. Because it loses energy as time goes on, according to the second law of thermodynamics. So it's losing energy, and it becomes into a bottom quark. Perfect. But bottom quarks cannot turn into top quarks because they don't have the necessary energy to decay into a top quark. Now, if bottom quarks were heavier than, or has more energy or mass than a top quark, the problem now would be that top quarks, it would be essentially switched or reversed. The top quarks cannot decay into bottom quarks, but bottom quarks can decay into top quarks. Okay. So, before we discuss further, let's talk first about Feynman diagrams. What are Feynman diagrams? Now, how do we visualize the decaying process of any particle? So, let's say by the decay of photons, or of course the decay of a top quark into a bottom quark. How do we do that? How do we visualize all that without using math? Well, we use what is called a Feynman diagram. Of course, named after its creator, Richard Feynman, one of the pillars of quantum physics. This was a remarkable man. He was really true, not just particle physics, the entirety of physics, all in all. So Feynman diagrams are diagrams that helps us describe what happens to a certain particle as time goes on. So it's not necessarily a graph, but it is a diagram nonetheless. So it really depends on the author, but sometimes they let the time axis be this way. So this is time. While some lets it go this way. This time. Now I'm going to use this convention. The time is running upwards when we're visualizing the process. I'm going to use red to denote the various particles. Now, it's important that I categorize various particles as fermions and bosons because the convention is very important. So conventions for traveling particles, because particles are obviously traveling through space, right? They create a line, and this line, in fact, is what we call a world line. Now, if you believe in string theory, and if string theory is to be believed, and that these particles are actually strings in space, they trace out what is called a world sheet. Okay, so if I'm not going to sidetrack further, now this here, of course, direction of where the particle is moving is dictated by an arrow or a tick mark, right, of where it's going. Some use this, well, I just going to use this convention, alright? Okay, so I'm going to use the one where the arrow's in the middle. There. So it's easier to see where it's going. Okay, so this type of arrow or line is used for or reserved for fermions. Okay, and then now a squiggly sine-like wave line is reserved for photons. Of course, photons act somewhat like waves, so therefore it would make sense to denote them, or, well, in a Feynman, denote them via a wave-like pattern or line. That would make sense. And also, this also denotes the W plus minus and Z bosons. So W or W plus minus, or the WZ boson. And this will be important when we discuss about actual decay of tops into bottoms. Okay. And then this like spring type pattern is reserved for gluons. then this broken line is reserved for the Higgs boson. Oh, I forgot to mention a while ago that the Higgs boson is the most important particle of them all. I'm not gonna go deep into what exactly the Higgs boson is, but of course it's a specific type of boson, but it is the center of all of this theory. It's very important actually. But yeah, I'm not gonna go deep into it. Okay, so let's say we want to collide to let's say that we want to collide to not really so actually okay. So let's say we wanna let's go straight to the point, and we want to show the decaying process, or what happens when a top decays into a bottom. So it goes like this. The diagram goes like this. And then there. That's the process. And this one is the W plus boson. Yeah. It is an E plus, an electron, and then this one, nu, or nu is an electron neutrino. Now neutrinos are part of the fermions, by the way. That's why we use this in notations here. And again, I'm not going to go deep into what neutrinos are, but these particles regularly pass by the Earth without ever affecting anything. In fact, there's probably one neutrino whizzing past you right now, and you just don't notice it, because these neutrinos are immensely small enough to travel past us. Okay, so this is what happens when a top decays into a bottom. It emits a W plus boson, and in which that W plus boson decays into an electron and an electron neutrino. Okay, so this is what happens. Now the same thing happens to a bottom quark, but instead, what is emitted is a W minus boson. And instead of it being a top, of course we cannot have the bottom decay into a top. It decays into an up quark. And this is a minus boson. Of course it stays an electron, and then this is also a neutrino. Unless I got something wrong here. So either way, there's always an electron and a neutrino emitted after the boson is emitted from this particle decaying. Okay. So it can only become an up or down quark, or charm quark, or strange quark, but the bottom quark can never be a top quark according to the second law of thermodynamics. Okay. So now you're thinking, what about collections of these particles? Now you're thinking, okay, if we have a top and a bottom, what about a switch, right? What's a switch in the context of quantum electrodynamics? Well, there are these things called mesons. And mesons are collections of quarks. So if you want to say M, it's a collection of quarks. And it can contain any two pairs of quarks, so long as it's not, any two pairs of quarks, as long as their anti-quarks are part. So every elementary particle has an anti-particle. So a reverse particle. So a proton has an anti-proton, a photon has an anti-photon, a quark has an anti-quark, a boson has an anti-boson, etc., etc. So, okay, mesons. Since mesons are able to give us a good way of pairing two things together, right? We want a superposition of tops and bottoms, right? That's essentially what a switch is, a top and a bottom. So there is a specific meson called a T meson that contains both. So let's pretend that this ball is the T meson that contains both a top and a bottom quark, as well as their anti-quarks. Of course, this balances out. The reason why they have anti-quarks here is because the total energy would equal to 0, and so it's balanced out. So that's a T meson. Now you may be thinking, okay, do you think that, is it possible for a T meson to decay into a top and a bottom? Well, yes. In fact, T mesons decay so fast that we're not able to study it properly. And some properties of the T meson are still pretty ambiguous at this point because it decays so fast. Now, what's the Feynman diagram of a T meson that decays? That contains both a top and bottom quark. Well, bear with me here, it might be a bit complicated, but I'm just going to draw the line here. T. Okay, let's start out with our T meson. So this is our Tm for T meson, and then it splits off into a top and a bottom quark, as well as their anti-quarks. I'm going to keep the T away from its anti-quark because we don't want them annihilating each other. And same thing with the bottom quark, we don't want them to annihilate each other, so we're going to keep them away. So these things, we're not going to mind the anti-quarks for now, but notice that, of course, like a while ago, the bottom quarks, and of course mesons are not just going to do that. So what we're going to want to do is send a photon its way, so that we can start the splitting process, because nothing's going to happen to this T meson unless we strike something with it. And it's to make sure that these bonds actually break and don't just split off into two groups. Okay? So yeah. So it's a P. And then so the bottom again decays into an up quark and then emits a W minus boson. The minus boson becomes an electron and an electron neutrino. And then the top here decays into a bottom, and then emits a W plus boson, which also becomes an electron and an electron neutrino. And then of course this bottom over here decays into an up quark, quark, and then emits a W minus boson, an electron, and a neutrino. This Feynman diagram is frankly a mess, but this is probably what happens. Okay. So I'm just going to list it down here. Actually, since it's a decay, a natural decay, it's happening on its own, and we actually don't need the photon to initiate the decay. So we can probably remove this now. Now again, this reaction is theoretical, okay? I believe the actual reaction is far different than this, but according to what we know at the moment, this is what it would look like, I presume. Again, do correct me in the comments if what I'm saying is wrong and what I'm doing is wrong, because I would really appreciate that. And your feedback or your correction will be put into a footnote in this new course or playlist. So there it is. The switch decay into a top and a bottom, and it will depend on chance whether stays top or stays at bottom. But it will require us to input some amount of mega electron volts to maintain that. Mega electron volts per C squared. Okay. So that'll pretty much be it for this lecture.